Hello dear students, welcome you all. In this lecture I am going to discuss about the laws of thermodynamics, right? Laws of thermodynamics are basically certain rules in thermodynamics that govern the relationship between the matter, energy, temperature and entropy, right? So if we want to describe a thermodynamic system completely, then there are certain rules which we called laws in terms of in case of thermodynamics, right? So we have four thermodynamic laws, right, which are known as zeroth law, first law, second law and third law, right? So these are the four laws that govern all the thermodynamic processes, right, in nature. So we will discuss one by one all of them in this lecture. So I am going to start with the first law, right? In fact, the first law is zeroth law, right? Zeroth law, then first law, then second, and then third. You can see here, zeroth law actually give the condition for the thermal equilibrium between two bodies. It says that if two objects A and B are in thermal equilibrium with C, then they are also in thermal equilibrium with each other, right? We will discuss it thoroughly. Then the first law, this give us the relation between the energy, amount of work and amount of heat energy, right? So it is basically a law of conservation of energy, and the zeroth law is basically gives us the definition of a temperature. Similarly, second law states that in all spontaneous process, the entropy of the universe increase. You can see here, this is a balloon, clear, inflated balloon. So if we left this balloon, then the air from inside the balloon will came out spontaneously, and this is the balloon now. But it is not possible that this balloon can get this position by spontaneously getting air inside. This is not possible, right? So this is basically the simplest demonstration of the second law. Otherwise we have two different statements of second law of thermodynamics. Similarly, this is the third law. You can see here we have contained a particular material inside this jar, right? It is a crystalline substance. If we decrease the temperature, then the motion of the atoms or molecules inside this material will decrease. If we go on decreasing temperature, ultimately their molecular motion or atomic motion will cease. They will come to rest, but that temperature will called as absolute zero temperature, a temperature of 0 Kelvin, or we can say minus 273.15 degree Celsius, right? So the value of entropy of a completely pure crystalline substance is 0 at absolute, right? You can see here. Now entropy is 0 here, right? So this is about brief about these four laws of thermodynamics. Now, right, we will come one by one to all of them, right? We have these four laws: zeroth law, first law, second law, third law, right? Now I'm coming to the first law. You can zeroth law, right? So you can see here in zeroth law of thermodynamics, clear? This is system A, this is system B. They are in contact separately with system C, clear? And you can see here that heat energy is flowing from system B to C and A to C, or C to A or C to B. It can be in that way. It means the system A and system B are going to be in thermal equilibrium with system C, clear? If I connect these systems, three systems in this way, and all of them have different amount of heat energy inside them, clear? Heat energy means energy of the atoms or molecules due to their motion, kinetic energy basically, right, acquired by the molecules or atoms. So if they have different heat energy, when we will have this arrangement, after some time A and C will have same amount of heat energy. Similarly, C and B will also have the same amount of heat energy. We can say that A and B are in thermal equilibrium with C, clear? So the a statement of zeroth law of thermodynamics states that if these two systems are separately in thermal equilibrium with system C, they should be in thermal equilibrium with each other. We can check it. If we bring these two systems in contact with each other, we can see there is no flow of heat energy from one system to another because they are already in a thermal equilibrium. Right. Now here it is very important. The question can arise that why we are calling it as a zeroth law of thermodynamics. Why it is not fourth? We have first law, second law, third law, and fourth law. Why it is zeroth law? Right. So the answer of this question is hidden in this picture. Clear? This picture is Ralph H. Fowler. Clear? He is the physicist who in 1935, clear, give a statement that every physical quantity must be measured in some numeric terms. Clear? So this is the year in which we got the term temperature. Clear? Prior to 1935, nobody know about the term temperature. So this is temperature is basically the term, clear, that tell us whether a system is in thermal equilibrium with the other system or not. Clear? And when the system is in thermal equilibrium, this is the physical quantity that is common among them. Clear? So Ralph Fowler has described this process, this physical quantity temperature. So in 1935 there comes the definition of this zeroth law of thermodynamics. We call it as zero because by that time 1935 we already have first, second and third law. They were already described. So if we rearrange at that time all these three laws, we modify the first law, then it will going to create a lot of chaos. So it was thought that we should give it name zeroth law, right? Because this is most fundamental. Zeroth law is the founding step for first, second and third law, because in first, second and third law the temperature is already included. Although we are not using the term temperature, but that quantity is already involved there, right? It means this thing has to be studied before going into first, second or third law. So that's why we give it the name zeroth law of thermodynamics, right? So I think now it is very clear what is zeroth law of thermodynamics, right? It tells us whether a system is in thermal equilibrium or not, and if a system is in thermal equilibrium with each other, then they must have a common physical quantity that is called temperature, right? You can see I have told you here that these two systems are in thermal equilibrium with C. So if now we remove these, after some time they will come in thermal equilibrium. If I remove A and V and join these together, right, then they will be already in thermal equilibrium, right? So no flow of heat energy will take place from A to V, right? It means A, B and C, all three bodies are in thermal equilibrium and they have same amount of heat energy. Clear? So that quantity that defined the measure of that heat energy is called temperature, right? So this is about the you can say zeroth law of thermodynamics, right? Now we can see how this zeroth law of thermodynamics is linked with the examples of daily life, right? You can see here the example that I want to discuss as the application of zeroth law of thermodynamics. When we measure the temperature of the body, then our body comes in thermal equilibrium with the thermometer. How? When we insert thermometer inside our mouth, initially the heat energy of the material inside the thermometer, like mercury, it is low as compared to the heat energy inside our body. So when we put thermometer inside the mouth, the heat energy tries to flow from our body to the thermometer. After some time, right, both the bodies will come in equilibrium with each other, and that time, what is the degree of heat energy, that will be indicated on a scale that is called temperature of the body. So remember, this is clear cut indication that our body and thermometer are in a thermal equilibrium. Similarly, we can measure the atmospheric temperature, all temperature measured for industrial applications. So basically all these applications are what? They are measuring the degree of equilibrium between the two systems, right? So this is about the zeroth law of thermodynamics. Now I am coming to the first law of thermodynamics. I told you that first law of thermodynamics is basically what? It is the law of conservation of energy in thermodynamics. When we add energy in a system, then that energy is utilized in two ways. One, it is used to increase the internal energy of the system. Second, it is utilized in doing the work. You can see here examples. Here we have chemical energy, that it is basically a firework cracker. When it goes up, it has chemical energy stored inside it. So when it bursts, it gives heat energy and sound energy. Clear? So energy changes from one state to another. Similarly, you can see here it is a fan. So electric energy is converting into mechanical energy. Here electrical energy is converting into heat energy. Clear? Here you can see it is a piston, clear, fitted with a movable crank or a wheel, flywheel. So when heat is added in this system, then this piston will expand outward and we will get mechanical energy. So heat energy will be converted into mechanical energy, right? So one thing is clear, that in nature energy cannot be created and cannot be destroyed, but it simply transforms from one form to another, right? So you can see here in all the examples. So this analogy is applicable in thermodynamics also. So when we add energy in a thermodynamic system, you can see various examples: electrical energy, chemical energy, mechanical energy, right? Here it is solar energy, right? Then again, so all these are examples that show us that energy is interchangeable among the different systems. Clear? So let's see what is the statement of this first law of thermodynamics. So according to first law of thermodynamics, the net change in the total energy of a system is equal to the heat added to the system minus work done by the system. You can see a equation here. This, clear? Delta E is equal to Q minus W. Even I can give you, I can write here. You must have heard of the first law of thermodynamics, that is dQ is equal to du plus dW. You might have heard first law of thermodynamics statement as it, but it is same thing that I have written, that we have seen on the screen. That is delta E is equal to, it was delta E is equal to Q minus W. So you can see here Q minus W. So it is same thing, you can see here, right? If I write it is in this way, du is equal to dq minus dw, same thing. What is du? Change in the internal energy of the system. dq, amount of heat energy added to the system. dw, amount of work done by the system, right? So the same thing. So this is the statement of the first law of thermodynamics. You can write it in this way also, you can write it in this way also. In this way, if I express it in PdV, clear, dq is equal to PdV, so it becomes this. So it will becomes du is equal to dq minus P dV in that case. So this is the different forms of first law of thermodynamics. Clear? So basically it is nothing but it is law of conservation of energy. Clear? Once again I am saying that when we add energy to a system, clear, then that energy can be utilized in two ways. One, in doing the work, and second, in increasing the internal energy of the system. Clear? Sorry. So you can see here, this is net change in the internal energy, what I said, right? So now I'm coming to the second law of thermodynamics, right? You can see here, this is an inflated balloon. So it is very clear from here that if we left this balloon as it is, after some time it will come to this situation. Clear? Air will escape from here, because here inside this balloon, air is feeling lot of pressure. It want to go away from it. So the system will transform to this spontaneously. Clear? But in nature it is not possible. This is the balloon, and if it happens that the air spontaneously go inside the balloon and it got inflated, so it is not possible. So this is the way of understanding the working of nature, right? That in nature we can say all the process or phenomena takes place in such a way that the disorder always increase. You can say when the air is trapped inside this balloon, it is more ordered. Gas molecules are close to each other, right? They are more ordered, but they escape from one another, then they become disordered. Entropy increase, right? So in first situation entropy increase, but in the second, if it happen, entropy will decrease, but this is not possible, right? So it means in nature there is always increase of entropy. You can see these systems that when you left these system, we have these two systems, right? And when we left this system, we remove this barrier, they will mix up and attain a equilibrium state. And the disorder, initially suppose they were in order, then after you will get disorder, right? So this is the same thing, but this can't come to this position spontaneously, that you will get ordered particle in two compartments. This is not possible in nature, right? So you can see here, when you left a cup of hot tea, then after some time it will get cooled, but it is not possible that heat will come from outside and it will heat the cup. This is not possible, right? So this is all about a second law of thermodynamics, right? Now I'm coming to the statement of the second law of thermodynamics. We have two statements, Kelvin statement and a Clausius statement, right? See here, Kelvin statement. It is impossible to construct a device, clear, which work on a single heat source and convert all of its heat completely into work. This is the Kelvin-Planck's statement. Clear? It simply say that a heat engine must exchange the heat with at least two thermal reservoirs, one at high temperature and other at a low temperature. Then only the heat engine will operate. Clear? It means if we have a heat engine, if I want to explain it, then it is impossible for that heat engine to convert all of its heat into completely work. Means 100% efficiency of the heat engine is impossible. When we will add heat to the system, some of the heat energy will be utilized in doing work and some will be utilized in increasing the internal energy, right? So it is somehow linked with the first law of thermodynamics also, but here we are connecting it with the heat engine, right? So it means perfectly 100% efficiency is impossible. Clear? So this is Kelvin statement. Clear? You can see here we have a heat source that add 100 joules of heat to the heat engine, right? And then it gives work of 100 joule. So it is not possible. Heat engine that violate the second law. This will violate the second law of thermodynamics. Clear? It is not possible. Clear? So this is the simplest. It is impossible to construct a device which work on a single heat source and convert all of its heat into completely work. Clear? This is Kelvin statement. Right. Now I am coming to the, you can see this example also. We have a hot body, we have a heat engine. This heat engine takes heat from this hot body 100 kilojoule, and then it do some work and reject the heat to the cold body, that is 60 kilojoule. Right. Now it is satisfying the first and second law of thermodynamics. Right? Because all the heat energy is not converting into work. It is doing work of 40 kilojoule and rejecting the heat of 60 kilojoule. Right? So this is Kelvin statement. Clear? Now I am coming to the Clausius statement. According to Clausius statement, it is impossible to construct a device that can transfer heat from a colder body to hot body without doing any work. So it is very simple. Heat cannot itself flow from colder body to hotter body. You can see in the nature. So this is the second statement of the second law of thermodynamics, and it was given by Clausius, right? So it is very simple, to understand. You know very well that this kind of situations don't exist in nature, right? We have to do work if we want to transfer heat energy from a colder body to hotter body, like in a fridge, like in a AC, where the work is done by the AC source, right? This is about the first law and second law of thermodynamics, right? Now I am coming to the third law of thermodynamics, right? So you can see here, we have some crystalline solid here that is contained inside this jar, and we decrease the temperature. So initially, the molecules or atoms of this crystalline solids are having some motion. So as we reduce the temperature, their motion go on decreasing, and as their kinetic energy decrease. So if we go on reducing this temperature, ultimately we will reach a temperature at which this molecular motion will cease. That temperature is called absolute zero temperature, right? So we can say it is 0 Kelvin or minus 273.15 degree Celsius. So this is the ultimate lowest temperature possible in the nature, and at this temperature there will be no disorder in the system, and the entropy of the system will become zero, right? So this is third law of thermodynamics. It is linked with the entropy, right? How we can reduce the entropy of the system, what is the lowest possible temperature in the universe. So all these things are linked with the third law of thermodynamics. But we know very well that we are not able to produce a temperature of 0 Kelvin in the universe. So it means in all natural processes, clear, it is impossible to reach the temperature of 0 Kelvin, because if we want to do that, then we have to do infinite amount of work, right? So this is about the third law of thermodynamics, right? I can explain it in this way also. You can see here why 0 Kelvin temperature is not possible, because we know according to second law of thermodynamics, if we want to extract heat from a system, we want to cool a system, then we have to do a work. So we are doing work and extracting heat from a system and making it cooler and cooler, and we are sending that heat outside, right? So if we want to approach the temperature of 0 Kelvin, we have to continuously do the work. We have to extract the entire amount of heat from that system. But here is one twist. The system is not 100% isolated. Some amount of heat will definitely enter from the outside inside the system. So you will keep on removing the heat, but you will not reach that a time when the total heat energy from that system will be extracted. So theoretically it is not possible, and experimentally also till now we are able to reach a temperature of 0.001 Kelvin but we are not able to approach a temperature of 0 Kelvin. So this is the third law of thermodynamics. It gives us about the law of increase of entropy and definition of absolute zero temperature, right? So this is all about these four laws of thermodynamics: zeroth law, first law, second law, and third law of thermodynamics. These are very important in understanding the entire thermodynamic systems, right? So thank you very much.